In this video, we're talking about how to find the derivative of a logarithmic function, and in this particular problem, we've been given the function f of x is equal to the natural log, or ln, of the third root of x cubed minus x. So when you're talking about taking the derivative of logarithmic functions, first of all, a logarithmic function is any function that involves the natural log, or ln. And when you're taking the derivative of a function like that, the most important derivative rule you need to know is that the derivative of natural log of x is 1 over x. So that's the most basic rule we're going to be working with. But most of the time, you're going to have something more complicated than just x inside of your logarithmic function here. And in that case, you're going to have to make sure that you remember to apply chain rule when you take the derivative, and we'll talk about that as we go through this example. You're also going to want to keep in mind your laws of logarithms. In this particular example, we're going to be using this law of logarithms to simplify the log, but oftentimes you'll be able to simplify the logarithmic function before you take the derivative using laws of logs. So let's go ahead and start tackling this problem. First of all, before we take the derivative, we're going to want to do everything we can to simplify the function. So we need to realize here that when we're taking the third root of anything, that's the same thing as raising whatever's inside this square root to the 1/3 power. So we can actually rewrite this function without changing the value at all. This function can also be written as the natural log of quantity x cubed minus x, the value that was underneath the square root, raised to the 1/3 power. So instead of taking the third root, it's the same thing as raising it to the 1/3 power. Now here's where our laws of logarithms come in. We know that the natural log of, let's just say, x to the n, when we have a base here, x, and some constant exponent, n, that we can pull that exponent out in front of the natural logarithm, and that n times the natural log of x is the same thing here. So in this case, we have this exponent 1/3. We can pull that out in front of the natural logarithm, so still not changing the value of our function at all. We bring that 1/3 out in front, and we say 1/3 times the natural log of x cubed minus x, and we haven't changed the value of the function, but we've simplified it significantly. Now with the function simplified to this point, we can go ahead and start working on the derivative. So if the original function is f of x, the derivative function is going to be f prime of x. And when we take the derivative of 1/3 times the natural log of x cubed minus x, that 1/3 is going to stay out in front. We're really just dealing with the derivative of this natural log function. Well, we know that the derivative of natural log of x is 1 divided by x. So if we just take the derivative of natural log of x cubed minus x, we can say that that derivative is 1 divided by x cubed minus x, because really what we're saying here is that this value inside of the natural log function, that goes to the denominator, where the numerator here is 1. Well, in our case, we have x cubed minus x inside of our natural log. That's going to go to the denominator, where the numerator is 1. But now we have to remember to apply chain rule, because chain rule tells us that we can't just ignore this inside function. We actually have to multiply by the derivative of the inside function. So in the simple case of the natural log of x, we know the derivative is 1 over x, but then chain rule would tell us you ignored the inside function x. You have to multiply by its derivative. Well, the derivative of x is 1, so we have to multiply this by 1, but of course multiplying by 1 doesn't change the value, so this still just ends up being 1 over x. But in this case, it will change the value. We have to multiply by the derivative of that inside function. So the derivative of x cubed minus x is 3x squared minus 1, so we have to multiply our result by that value. And now this is going to be our derivative. All we have to do is simplify as much as we can. So we're going to say f prime of x is going to be equal to, this 3x squared minus 1 is going to go into the numerator. We have that multiplied by 1, multiplied by 1, so we just end up with 3x squared minus 1 in the numerator. And then in the denominator, we have 3 times quantity x cubed minus x. We can factor an x out of the denominator here, so we want to go ahead and do that, and we'll say f prime of x is going to be 3x squared minus 1 divided by 3x times x squared minus 1. And this will be our final answer. This is the derivative of the original function. Now, just one quick note. You might be tempted to say, oh, I can cancel this x squared minus 1 in the denominator with the x squared minus 1 in the numerator. But you actually can't do that because there are no parentheses around this x squared minus 1. And if you cancel that out, it would be like saying there are parentheses around this so we can cancel the factor of x squared minus 1. But if there were parentheses, it would be like this 3 out in front is multiplied by this negative 1, and that's not not the case. That 3 isn't multiplied by the negative 1, so you can't cancel the x squared minus 1. You also can't cancel this factor of 3. You might say like, oh, I can cancel this 3 in the numerator with this 3 in the denominator, but that would be like saying 3 is multiplied by everything here in the denominator, which it is, but that it's also multiplied by everything here in the numerator, which it's not. This 3 is not multiplied by the negative 1. And when you cancel something, you have to cancel it out of every term. We can't pull it out of this negative 1 because the 3 is not multiplied by the negative 1. The only way you'd be able to pull out a 3 is if you had 3x squared here minus 3, and then we could take a 3 from each of the two terms in the numerator and from the single term in the denominator. But that's not the case. So this is going to be our final answer for the derivative of the logarithmic function.